In this lecture, we're going to look at counterexamples to the Noetherian condition. Firstly, let's look for a ring that is not Noetherian, a non-Noetherian ring. A very obvious example of a non-Noetherian ring is to look at the ring of polynomials in infinitely many variables. So you take R to be, just fix a field K, and you take infinitely many variables x1, x2, x3. So here K is any field. What does this mean? Well, an element of this ring is just a finite set of monomials in the variables x1, x2, x3. So finite sums of expressions of the form a xi1 to the d1, xi2 to the d2, xir to the dr. So we just take a finite sum of expressions of the form. The result is called a polynomial in infinitely many variables. So each monomial in this is still finite, and you're still taking only a finite linear combination of such monomials. Now this ring is non-Noetherian because you can construct what I call a strict ascending chain of ideals. So let IR be the ideal generated by x1, x2 up to xr. So I'll just call this x1, x2. So what this is it's the set of all elements of R of the form x1 times f1 plus xr times fr, where f1, f2, fr are arbitrary elements of R. And this is the general notion of an ideal generated by a finite set of elements. And clearly these are ideals, and we have I1 is strictly contained in I2, which is strictly contained in I3, and so on. So we have a strict ascending chain of ideals showing that R is not a Noetherian ring. We've seen that when R is Noetherian ring, then every submodule of a finitely generated R module is again finitely generated. When R is not a Noetherian ring, you can always find a finitely generated R module which has a submodule that's not finitely generated. To see this, let's take the same, I'll just illustrate it using the same example of a non-Noetherian ring. R equals k x1, x2, x3, the polynomials in infinitely many variables. So let's take as an R module R itself. Think of R as an left R module. Now this is a finitely generated R module. It is just generated by a single element, the unit of R. Now in this R we had strict ascending chain of ideals. Let I be the union of these ideals. Then I is again an ideal, and so it is a submodule of R. It's an R submodule. Right, we've discussed this before, that ideals of R become submodules of R when we regard R as an R module. Then I claim that I cannot be finitely generated. Why is that? Suppose it is so generated as an R module. Suppose it is, then say I is generated by let's say some elements m1, m2, mn, then there exists a large number capital N such that mi belongs to in for all I equals 1 to n, because each mi belongs to some IR, and then it belongs to all the ISs for s greater than R. So beyond some point each mi belongs to some IR and all the IRs that come after it, and just take the largest of these numbers and all the mi's will belong to one of the ideals in. But then that means that in is equal to I, because the mi's actually generate I. But this contradicts our assumption that in is properly contained in in plus 1, which is contained in I. So I is always going to be a submodule of finitely generated R module that is not finitely generated. Okay, in this example, of course, I was keeping in mind the ring R of polynomials and infinitely many variables, but I didn't actually use that anywhere. I just used the fact that R has a strict ascending chain of ideals. So this works for any non-Noetherian ring R. Every ring, whether Noetherian or not, admits non-Noetherian modules. Let's look at a construction of that. So take R to be any ring, and take M to be the module, which I will write as follows: n equals 1 to infinity R. So the direct sum of infinitely many copies of R. What this is it's the space of all sequences Rn. N goes from 1 to infinity, so it's like sequences R1, R2, R3, such that Rn is equal to 0 for all but finitely many n. Then inside M you can look at Mn or Mr, let's say, to be the submodule consisting of sequences Rn such that Rn equals 0 for all n greater than or equal to R. Then we have M1 is properly contained in M2, properly contained in M3, etc. So this is a strict ascending chain. Therefore, M is not an Noetherian R module. Another interesting example of a Noetherian R module, non-Noetherian R module, is something you're all very familiar with. Just take R to be the ring Z of integers and take M to be the rational numbers, but don't think of it as a field, think of it as a Z module. Okay, so clearly you can add two rational numbers, you can multiply a rational number by integer to get an integer, to get another rational number, and that gives the set of rational numbers the structure of an R module. Now I claim that this R module is not Noetherian. How? I'll construct you a chain, a strict ascending chain. Take Mn to be all rational numbers which are of the form 2 to the minus n times an integer. Then these are all rational numbers whose denominators are divide 2 to the power n. And so clearly you have M1 properly contained in M2, properly contained in M3, and so on. This is a strict ascending chain. And you can easily check that these are actually submodules of Q, Z submodules of Q. So Q is not a Noetherian Z module. What are the finitely generated submodules of Q? So suppose we have a submodule of Q which is generated by, let's call this submodule U, and U is the submodule generated by some rational numbers Q1, Q2, Qn. Then I can multiply out all these rational numbers by some large integer, say the product of their denominators. There exists n belongs to Z such that nq1, nqn are all integers. Now you take GCD of these integers, that's going to be an integer, and divide it by n and call that Q. So let Q be 1 over n times the GCD of nq1, nq2 up to nqn. Then I leave it as an exercise to you to show that U is just the Z submodule generated by Q, i.e. U is just Z times Q, all the integer multiples of Q. So every finitely generated Z submodule of Q is just generated by one element.